is this information about function notation today. Okay, so here we go. Function notation. This is the way that we represent functions. It's letters that we use. Function notation. All right, so the notation is like this. We say y is equal to f of x. Have you ever seen this before? F with an x inside. Y is equal to f of x. This defines a function named f. This defines a function named f. Okay. This is read as y as a function of x. That's what we would say. Y as a function of x. Where the letter x is your input value. And the letter y, or the f of x part, is the output. Okay. So if we broke that down, we would have y equals f of x, where x is the input. And f of x is the output. Are y'all following that?
No.
Not at all. No. Input and output. Okay, so this is a hard no for you guys, right?
Maybe I just need an example. Dang, I can't talk.
Did we get it written down?
Yeah.
Let me get here. Okay, so example 3 has D as the number of days, and we're going to use that as a function of m. D is f of m. D is equal to f of m, where m is the month. That's going to be my input. Absolutely. I'm sorry. You need a pencil? You got a pencil? M is the month. Now, depending on what month I put in this place, I'm going to have an output of number of days. Do you see that? So the number of days depends on the input, the month. So let's say F of January. So input January. Number of days as a function of January would be what? 31, right? Everybody got knuckles? Can you count them? January, February, March. Y'all know this, the knuckle thing, right? So 31 in January. Do you know this? Teach them. The spaces have 30? And the knuckles have 31?
Oh, so it's like every other month.
Uh-huh. And then you start over on the knuckles. 31, January, February, March, April, May, June, July. And then August. Well, in Spanish, I guess, maybe different names. But it still works. You got 12 months in Spain?
Yeah.
Well, then it works. Okay, so let's look at F of September. September. F of September. 30. 30 days had September, April, June, and November. 30 days for those. How about F of February? Unless it's a leap year. Let's do F of February 2024. It's 29. It's a leap year. Britton, you're learning a whole bunch of stuff today. This is how this works, okay? My output number, is going to be the actual number, D, days. How many days? That is going to absolutely depend on, that's why we call it the dependent variable, the input, which would be months. Okay, so it's like a machine. I input information into the machine and it outputs information based on what my input is. Is that helping? Is that making more sense here? Okay. So let's go on to example 4. And example 4 says n, so this is example 4. N is equal to f of y. This gives the number of police officers. This function gives the number of police officers in a town in year Y. So let's talk about this for just a second. What's my input? Y. The year. So depending on the particular year, there would be how many, what? How many police officers? And what's the dependent variable is going to be in the number of police officers, whereas the independent variable or the input is going to be the year. You understand that years would be independent because time's just going to keep ticking, right? It doesn't depend on how many police officers there are. But the number of police officers may depend on the input, the year. Are we cool with that? Okay, so help me understand this statement. This says f of 2005 is equal to 300. What is that saying? In the year 2005, what? Yeah, there were 300 police officers. Cool beans? Is that feeling better? What if I just said this? F of x equals 750. What might I be saying? Yeah, in the year X, whatever variable that might be, there were 750 officers. Okay. What if I said F of 2023 equals X? There's an unknown amount in 2023. I would have to go to some resource, a data table or a spreadsheet or something like that. Okay, but that's the question it's asking that. So the first question was asking, in what year are there an output of 750? The second question says, in 2023, there are how many police officers? Can you see that they're both using the same data set, but asking two different questions? Cool? Okay, moving on. I think we're handling this. Number 5, it says this evaluate the table and tell if they represent any functions. So I took pictures earlier today. Nope, that was not it. Cancel. I took pictures from the textbook and I was trying to see if we could get some tables up and running that we could look at. No, I did not take good pictures. Okay, so I'm just going to write down some tables here. I really tried. I have good pictures of other things, but not example 5. I have a picture for example 6, just not number 5. Okay, so given a table. So in a table, I've got a column for input and I've got a column for output. These are directly coming out of this textbook. In the input column, I have 2, 5, and 8. In the output column, I have 1 and 3 and 6. And the question is, does this represent a function? Maisie said yes. Why? Why is this a function? No x is repeating. Okay, so yes, this one is a function. Because if I look at my inputs, for every input, there's only one output. Yeah? Okay, let's try another one. Input, output. Let's do 1 and 5 and 5 and 0 and 2 and 4. Yes, a function or not a function? Not a function because the input 5 has 2 outputs. If I were looking at that as ordered pairs, I would have a 5, 2 and a 5, 4. And that can't happen. I cannot have 2 outputs for the same input. 5 repeats. Cool? Any other questions on that? So in your homework, you're going to have a whole bunch of tables. And you're going to have to identify which ones are functions and which ones aren't. Okay, those are easy, fast. All right, example 6. This is called evaluating a function at a specific value. Let's see. Still no. Evaluating functions at specific value. Okay, so they start out by telling me this overarching function f of x is equal to x squared plus 3x minus 4. Anybody know what kind of function this might be? What's the name of this type? A quadratic function. How do you know it's quadratic? Because it has x squared. This is a quadratic. Is it a monomial, a polynomial, a trinomial, a binomial? It's a quadratic trinomial. Okay. It's got 3 terms. That's what that means. It's got 3 terms. Okay. It's in the form of ax squared plus bx plus c. Could you factor it? In theory, could you? Right? I mean, it's quadratic, so that's how we would solve it. We would factor it, if possible. If not, we could complete the square, or we could use the quadratic formula. Lots of stuff we could do to this guy. But you need to see that it is a function because of the way that they've written it. Notice that they didn't say y equals x squared plus 3x minus 4. Okay? This graphs a quadratic equation. The picture, if I were to graph this thing, probably looks something like this, and it's probably going to be moved a little bit off the y-axis, and you'll know why later. But it probably looks like this, a little bit. Okay, it's positive, it opens up. But the reason they wrote it in function notation is that I can evaluate this function at any given value. Okay, so what they want you to do for part A is they want you to find f of 2. Meaning find the output when the input x is 2. So what that means is everywhere that I see 2, I'm going to open parentheses and put a 2 in its place. We're substituting. We're not doing the big long substitution method that we learned before Christmas. We're just substituting into this function. Instead of x, we're going to put a 2. And we're going to evaluate. This 2 squared is what? 4 plus 6 minus the 4. So what's f of 2? Excuse me. Excuse me. F of 2 equals 6. That means when x is 2, I should get 6. I'm really sad because mine's not going to be looking like this at all on my picture. I'm going to erase my picture. I just tried to throw a graph up there. That's not at all what it looks like. F of 2 is 6. Benedict's laughing at me. It's okay. It's fine. I erased it. It's gone.
What did he say?
He said, I didn't laugh.
He doesn't laugh.
Ever. How would I write f of a? So every x gets taken out, and every time I see x, I write a instead. Okay, so this is going to be a squared plus 3a minus 4. A squared plus 3a minus 4. Not too bad. Okay. What if they wanted me to find part C? It says f of a plus h. Yeah, instead of x, I put in a plus h. Are we doing okay with this? I could simplify it. I could see right here that this a plus h squared business could be stretched out. It could be expanded, right? I don't call it a squared plus h squared. I don't get to distribute that square. I could stretch it out as a plus h times a plus h, right? In which case I would have a squared plus, so that's a times a, and then a times h and a times h. I'm going to get two of those. 2ah, and then on the end, plus h squared, plus 3a, plus 3h, minus 4. This would be the expanded version of f of a plus h. Y'all following that? Okay. So that's the benefit of function notation. I love function notation because it allows me to see clearly what I'm swapping in for x, right? And this allows me to find any value of y, given any value of x. Any input, I can find any output. I love it. All right, let's go on to example 6. Say again.
Never mind. I thought we were on example 6.
Example 7, you were right. Look, y'all, I've lost it. Example 7. It has happened. I've officially gone crazy. This function is called h of p. You'll miss out, but you can. H of p equals p squared plus 2p. Let me get you a hall pass. P squared plus 2p. Write that down really quickly. And then your instructions say find h of 4. Find h of 4. So what are we going to do? Yeah. We're just going to plug in 4 for p and see what happens. Say it louder. 24. You were right. He said 16 plus 8 is 24. So h of 4 equals 24. No problem? Okay. Here's example 8. H of p is p squared plus 2p. Solve for h of p equals 3. And I want you to notice it's so subtle, but the nuance is huge. The difference is huge. In example 7, they place the 4 in place of x, or in place of p. In example 8, h of p is set equal to 3. So I'm not going to put in 3 into the function. I'm going to set the function equal to 3 and solve it. Can you see the difference? Okay, it's really, really slight. The word up here says find h of 4, but you see that that 4 is in the input position. Here, h of p equals 3. You can see that the 3 is in the output position. So the question here is, what is p when h of p is 3? Can you see the difference? It's actually huge. I mean, it's the exact opposite. Am I plugging in or am I solving? Two different things. Okay. How do we go about solving this particular equation? What kind is it? P squared plus 2p equals 3. What kind is it? It's quadratic. How do you know it's quadratic?
P squared.
Because it's b squared. So how do I solve a quadratic equation? You could do factoring. How? What do we need to do first? Yeah, set it equal to 0. Set it equal to 0 first. So what you got here? 0. Resist the urge when you see a quadratic equation to start trying to factor out a p and do some weird stuff. It's not going to work for you. Your move here is set it equal to 0 and then either try to factor it, go into the quadratic formula, graph it. Y'all don't know how to do that yet, but. So we need factors of -3 that make 2. 3 and -1. So we've got p minus 3 and p plus 1. Both of those equal 0. So what are my answers here?
Wouldn't it be P plus 3 and P minus 1?
Yes, p plus 3 and p minus 1. You're right. Because we got to make a positive 2. Good call. P plus 3 and p minus 1. So p equals -3 and p equals 1.
That's how we got to answer P plus P and P.
So there are 2 times when this happens, graphically speaking. 2 times when the function is equal to 3. And the input and output relationship on example 7 is 4, 24. Yeah? We do okay on that? I think I want to pause right here on the video, and I'd like you to get a calculator because I think this is important that we understand exactly what just happened with this graph. Okay, so get a calculator.
Why are we grabbing?